Since the dawn of aviation, humans have relentlessly pursued higher and higher altitudes. Early aviators, driven by adventure and the pursuit of records, quickly learned that thinner air at higher altitudes presented both challenges and opportunities. The quest for altitude led to innovations in engine technology, aircraft design, and oxygen systems, paving the way for the development of specialized aircraft capable of soaring to the edge of space. These high-altitude aircraft, often operating in the stratosphere, have played pivotal roles in military reconnaissance, scientific research, and even space exploration. The desire to reach for the stars led to the development of specialized aircraft like pressurized cabins and powerful engines. The jet engine, a revolutionary breakthrough in aviation, proved particularly well suited for high-altitude flight. Its ability to generate significant thrust in the thin air of the stratosphere opened up new possibilities for high-altitude aircraft. The jet engine, coupled with advancements in aerodynamics and materials science, enabled the development of aircraft capable of sustaining flight at altitudes previously unimaginable. The pursuit of high-altitude flight has not been without its share of challenges and setbacks. The unforgiving environment of the stratosphere, characterized by thin air, frigid temperatures, and intense solar radiation, pushed the limits of both human and technological capabilities. Early high-altitude flights were fraught with danger, as pilots contended with hypoxia, decompression sickness, and the ever-present risk of mechanical failure. Yet despite these risks, the allure of exploring the unknown and pushing the boundaries of flight continued to drive innovation and progress in the field of high-altitude aviation. Among the most iconic high-altitude aircraft is the Lockheed U-2, a single-engine reconnaissance aircraft renowned for its ability to operate at extreme altitudes. Developed in the 1950s, the U-2 was designed to overfly Soviet airspace during the Cold War, gathering vital intelligence on Soviet military capabilities. Its distinctive long, narrow wings, resembling those of a glider, provide exceptional lift, enabling it to maintain flight in the thin air of the stratosphere. The U-2's lightweight design and powerful engine allow it to reach altitudes exceeding 70,000 feet, placing it well above the reach of most enemy aircraft and surface-to-air missiles. Another notable high-altitude aircraft is the Northrop Grumman RQ-4 Global Hawk, an unmanned aerial vehicle, UAV, designed for long-endurance, high-altitude surveillance missions. The Global Hawk, with its distinctive bulbous nose housing a sophisticated sensor suite, can fly for over 30 hours at altitudes exceeding 60,000 feet. Its ability to operate autonomously for extended periods and cover vast distances makes it an invaluable asset for military and intelligence-gathering operations. The Global Hawk's advanced sensors can collect high-resolution imagery, intercept communications, and provide real-time surveillance over large areas, making it a vital tool for modern warfare and intelligence gathering. While the U-2 and Global Hawk represent the pinnacle of manned and unmanned high-altitude aircraft, respectively, numerous other aircraft have been designed for operations in the stratosphere. The MiG-25 Foxbat, a Soviet-era interceptor, was designed to intercept high-altitude bombers and reconnaissance aircraft. Its powerful engines and robust airframe enabled it to reach speeds exceeding Mach 3 and altitudes exceeding 90,000 feet. The SR-71 Blackbird, another iconic American reconnaissance aircraft, was renowned for its speed and altitude capabilities, reaching speeds exceeding Mach 3.3 and altitudes exceeding 85,000 feet. These aircraft, with their advanced capabilities and unique designs, highlight the diverse range of applications for high-altitude flight. While high-altitude aircraft are often associated with military reconnaissance, they have proven invaluable in a variety of other roles. Scientists have long recognized the unique vantage point offered by high altitudes for conducting atmospheric research, astronomical observations, and Earth observation. High-altitude aircraft can carry sophisticated instruments to measure atmospheric conditions, collect air samples, and study weather patterns. Their ability to operate above the majority of the Earth's atmosphere also makes them ideal platforms for astronomical observations, providing clear views of the cosmos unobstructed by atmospheric distortion. High-altitude aircraft have also played a crucial role in disaster relief and environmental monitoring. In the aftermath of natural disasters, such as hurricanes, earthquakes, or volcanic eruptions, high-altitude aircraft can provide vital information on the extent of the damage, assess the needs of affected populations, and assist in search and rescue operations. Their ability to cover large areas quickly and provide real-time data makes them invaluable tools for disaster response. Similarly, high-altitude aircraft are increasingly being used for environmental monitoring, tracking deforestation, monitoring air quality, and studying the effects of climate change. The use of high-altitude aircraft for scientific research has led to numerous breakthroughs in our understanding of the Earth's atmosphere, climate, and the universe beyond. For example, data collected by high-altitude aircraft has been instrumental in studying the ozone layer, tracking the movement of pollutants in the atmosphere, and monitoring changes in Earth's ice caps and glaciers. High-altitude aircraft have also provided valuable insights into the formation of hurricanes, the dynamics of severe storms, and the long-term effects of climate change on our planet. Peering into the unknown high altitude and scientific discovery. High-altitude aircraft have proven to be invaluable tools for scientific discovery, particularly in the fields of astronomy and astrophysics. Operating above the Earth's atmosphere, these aircraft offer astronomers a clear and unobstructed view of the cosmos, free from the distortions caused by atmospheric turbulence. This unique vantage point has allowed scientists to make groundbreaking observations of distant stars, galaxies, and other celestial objects, leading to new insights into the nature of the universe. One notable example of the scientific contributions of high-altitude aircraft is the Stratospheric Observatory for Infrared Astronomy, or SOFIA. A joint project between NASA and the German Aerospace Center, SOFIA consists of a modified Boeing 747 SP aircraft carrying a reflecting telescope. Flying at altitudes up to 45,000 feet, SOFIA can observe infrared radiation from celestial objects that is blocked by Earth's atmosphere. This capability has allowed astronomers to study the formation of stars and planets, the composition of interstellar gas clouds, and the supermassive black hole at the center of our galaxy in unprecedented detail. High-altitude aircraft have also played a crucial role in studying the Sun. The NASA WB-57F, a high-altitude research aircraft, has been used to observe solar flares and coronal mass ejections, providing valuable data on the Sun's activity and its impact on Earth. These observations have helped scientists better understand the processes that drive space weather, which can disrupt communications, navigation systems, and power grids on Earth. By studying the Sun from high altitude, scientists can gain a clearer picture of its behavior and develop better forecasting models to predict and mitigate the effects of space weather events. Pushing the boundaries. Advancements in high-altitude technology. Advancements in aerospace technology continue to push the boundaries of high-altitude flight, enabling aircraft to reach even greater altitudes and operate for extended periods. New materials, such as lightweight composites, are being used to construct aircraft that are both strong and lightweight, reducing fuel consumption and increasing range. Advanced engine technologies, including scramjet engines and hybrid propulsion systems, are being developed to power the next generation of high-altitude aircraft, enabling them to reach hypersonic speeds and operate at the very edge of space. One promising area of research is the development of solar-powered high-altitude aircraft. These aircraft, powered by electricity generated from solar panels, have the potential to stay aloft for weeks or even months at a time, performing persistent surveillance, communication relay, or scientific research missions. The lack of a need for refueling would significantly reduce operating costs and increase the flexibility and endurance of high-altitude platforms. Solar-powered aircraft could also play a vital role in providing communications and internet access to remote areas, bridging the digital divide and fostering economic development. Another area of focus is the development of autonomous high-altitude aircraft. These aircraft, capable of flying and carrying out missions without human intervention, would offer significant advantages in terms of cost, endurance, and risk reduction. Autonomous systems could be used for a wide range of missions, including surveillance, reconnaissance, environmental monitoring, and communications relay. However, the development and deployment of autonomous high-altitude aircraft also raise important ethical and legal considerations related to safety, privacy, and the potential for misuse. The future is up high-altitude aviation in the 21st century. As technology continues to advance, the future of high-altitude aviation looks bright, with a plethora of opportunities and challenges on the horizon. High-altitude aircraft are poised to play an increasingly important role in a wide range of fields, from military operations and intelligence gathering to scientific research, disaster relief, and even commercial applications. The ability to operate at extreme altitudes offers a unique vantage point for observing the Earth and the cosmos, collecting valuable data, and conducting experiments that would be impossible from the ground. One of the most exciting prospects for high-altitude aviation is the development of hypersonic aircraft capable of reaching speeds exceeding Mach 5. These aircraft could revolutionize air travel, reducing travel times between continents from hours to minutes. Hypersonic aircraft could also be used for rapid response military missions, space tourism, and even point-to-point cargo delivery. However, significant technological hurdles remain in the development of hypersonic aircraft, including the challenges of high-speed flight, thermal management, and propulsion systems. Another area of growth for high-altitude aviation is the commercial sector. Private companies are developing high-altitude platforms, such as balloons and airships, for a variety of applications, including telecommunications, internet connectivity, Earth observation, and even tourism. These platforms offer a cost-effective and flexible alternative to satellites for providing coverage over large areas. As technology advances and costs decrease, we can expect to see a proliferation of high-altitude platforms in the commercial sector, driving innovation and creating new opportunities in a variety of industries.